Welcome to Cosmic Veil. I'm so glad you found your way to my observatory tonight. Before we start scanning the sky, I'd love to know where on Earth you're listening from. Share your location in the comments if you'd like. If this is your first time here, a gentle tap on that like button and a quiet subscribe would mean the absolute world to me. It helps other sleepy stargazers find our community, and if you are already subscribed, thank you. Your support genuinely keeps these slow cosmic journeys going. Now, I genuinely hope these astronomical facts aren't so thrilling that they keep you awake. But if they do, well, at least you'll have something beautiful to drift off to while you wait for sleep to finally wash over you. Tonight, as the world outside my telescope goes still, you and I are going to explore a question as massive as the night sky. Can human minds truly grasp the size of the cosmos? We call things big every day. A tall tree, a massive city, a huge mistake. The word rolls off our tongues so easily, just like far or even infinite. But honestly, we rarely picture anything close to the actual truth. Especially when tracking the universe. The simple truth is, human brains just were not built to process this kind of overwhelming scale. We evolved to judge the distance to the nearest tree branch, or guess how large a predator looks standing across a wide open field. Meters, maybe a few kilometers, that is the scale we handle best, the familiar zones, but out there in the freezing void beyond Earth. Distances explode into millions, then billions. We are talking numbers that don't just break human imagination, they completely laugh at it. So let's take a slow journey outward together. We will start from the dirt beneath your feet and push toward the edge of the known cosmos. We will drift past planets and ancient stars. Glide right through massive galaxies and cosmic webs, floating deep into regions where astronomy blurs into philosophy and space turns into sheer poetry. I am not looking for hard answers tonight. Honestly, there might not be any. Just treat this as a gentle float through the dark, a chance to sit beside these massive astronomical mysteries and admire their quiet beauty. Because my years looking through lenses taught me this. The most human thing isn't perfectly understanding the universe, it is simply being amazed by it. When you try to picture a long distance, what pops up? A walk down the block, a long road trip, or flying over the ocean. We understand those scales pretty well because we live them. They fit neatly into a normal human lifetime. A simple meter, a single kilometer. We easily picture these, feeling the miles pass under our own feet or blur past a rolling car window. But the second you break Earth's atmosphere, all those comforting measurements totally fall apart. Deep space ignores our tiny rules. It is not just huge, it is, quite literally, astronomically massive. Let me tell you, measuring the cosmos with Earth-sized rulers feels exactly like trying to drain the entire Pacific Ocean with a tiny teaspoon. Let us start with something right in our backyard, the distance from Earth to the Moon. It sits roughly 384,000 kilometers away. It sounds massive, but your brain can still somewhat grasp it. That is like flying laps around the Earth almost 10 times in a row, totally manageable. But now look toward the Sun. That is roughly 150 million kilometers away. That gap is so huge that sunlight, pushing the absolute speed limit of physics, still takes over 8 minutes to hit my telescope. This exact distance is our gold standard. We astronomers call it 1 astronomical unit. It is a brilliant little shortcut for mapping our local solar system. Mercury orbits near 0.4 astronomical units, Jupiter at 5.2, and distant Neptune hits 30. These clean numbers help us pack the vastness into bite-sized chunks, at least temporarily. But the second my telescope looks past our solar system, those handy units just crumble. The absolute closest star to us is Proxima Centauri, a glowing red dwarf over 4 light-years out. In astronomical units, that is 268,000. That isn't a convenient number. I'd need a painfully large spreadsheet. So enter the light year. Despite the confusing name, a light year does not measure time, it measures physical distance. It is the raw distance light travels through a dark vacuum in 1 Earth year. Sprinting at 300,000 kilometers a second, the total gets wild fast. In just 1 year, a single light beam blasts across nearly 10 trillion kilometers. That is 1 light year, just one. So when I log Proxima Centauri as 4 light-years distant, I mean the glow hitting my lens tonight actually left that star over 4 years ago. If it exploded tonight, don't worry, the physics say it won't. We wouldn't see a single spark for another 4 years. This means the light year isn't just a cosmic ruler, it is literally a working time machine. Every time you and I peer into the dark night sky, we aren't seeing the universe as it is today. We are seeing its ghostly past. The deeper I point my telescope, the older the light gets. We aren't just observing empty space up there. We are watching deep history play out backwards. Now for the truly curious or mathematically brave, there is another massive unit we astronomers use, the parsec. For us astronomers, a parsec equals 3.26 light years. I calculate it using simple trigonometry, watching how close stars seem to drift against the deep sky while Earth orbits the sun. It's incredibly handy for my daily math. But honestly, if you and I want to picture the sheer scale of space, a light year feels so much easier to grasp. At least in relative terms, but no matter which cosmic ruler I pick, kilometers, astronomical units, or parsecs, I always hit the same wall. The distances become far too vast to actually picture. I can record billions of kilometers or millions of light years in my logs, but those massive figures just don't carry any real weight in our human minds. The true scale slips right through our understanding, just like water spilling through your fingers. Our brains were built for a planet where the farthest horizon sits maybe a few dozen kilometers away. A walk of 2 miles was a trek, so naturally, trying to visualize 100,000 light years. The span of the Milky Way, or the 13.8 billion years of cosmic history, feels less like hard physics and more like abstract poetry. Yet this is exactly why I need these rulers. They let us push the boundaries of human perception just a fraction further into the dark. They give us a way to organize the unimaginable. These tools build a fragile bridge between our quiet Earth and the cold, sprawling void above. I find a strange comfort in knowing that, even if I can't physically touch a light year or step across an astronomical unit, we can still calculate them, map them out, and cast our thoughts into the deep, trying our best to make sense of the dark. Perhaps that's the true purpose of my work. We aren't shrinking the cosmos down to fit on a chalkboard. We're stretching human curiosity upward just enough to graze the stars. Let's look at this together. The universe enforces a strict speed limit, no exceptions. No matter how advanced your spacecraft is, how much fuel you burn, or how hard you push the engines, nothing outpaces light. Never in the cold, quiet courtroom of astrophysics, the speed of light is an absolute, final verdict. Light shoots through a vacuum at nearly 300,000 kilometers per second. That could lap Earth 7 times before you exhale. It is the absolute cap for moving energy or data across space. It's not just fast, it's the bedrock. Every natural law I study is tied to this exact speed. Even Einstein's famous E equals mc squared leans entirely on it. That letter C, that stands for the speed of light, but it's far more than a simple metric. It is quite literally the hardware of reality. And this is where my nightly observations get beautifully weird. Since light beams are so steady, my colleagues and I use them to map out deep space. But the moment we do, reality shifts. Time and distance begin to melt into one another. Down here on Earth, they are totally different things. You could hike 5 kilometers in an hour or drive it in 5 minutes. But through my telescope, that distinction vanishes. When I log a star as 1 light year away, I mean the glow takes a whole year to cross the void. That physical gap is roughly 10 trillion kilometers, give or take. Yet by using the clock to measure the ruler, we end up talking about both at the exact same time. I literally cannot measure how far a galaxy is without also stating how long ago its glow departed. This cosmic speed limit totally warps our human sense of time. When you gaze up at the moon tonight, you're seeing it as it existed just over 1 second ago. That is exactly how long the reflection took to reach Earth. The sun sits further out, roughly 8 light minutes away. So the warm rays hitting your face on a quiet afternoon actually left the solar surface while you were still brushing your teeth. Now point the telescope deeper. The glare from Sirius, the brightest star in our night sky, spent 8.5 years crossing the dark. The Andromeda galaxy, over 2.5 million years. That's no recording error. I see Andromeda not as it exists tonight, but exactly how it looked long before modern humans ever walked the Earth. Every single star I log, every faint smudge on the glass is an ancient echo. Space isn't just an empty backdrop, it is a literal time machine. Light delivers cosmic postcards from dead stellar systems, but they are never current. They arrive terribly late, sometimes by billions of years. That makes my observatories actual time machines. The deeper into the void I focus the lens, the older the photons I collect. My team has photographed infant galaxies whose light has been drifting for over 13 billion years. These are direct views of a baby universe, captured long before our sun or tiny blue planet ever formed. That is the beautiful, mind-bending gift of this job. It forces us to chart the sky in 4 dimensions, not just where a star is, but when. Because not even light outpaces the clock, it simply drags its ancient memories forward, one single second at a time. You and I can test this right now. If our sun suddenly vanished, not just faded, but entirely ceased to exist. My instruments wouldn't register a thing for over 8 minutes. The grand illusion would hold perfectly. The sky would stay bright. The world would keep turning, blissfully unaware, as those final sunny photons made their 8-minute commute through the dark vacuum. The sun's parting message would already be rushing toward my observatory at the only speed it knows. That holds true for everything I study. My eyes never perceive the present. I only catch delayed broadcasts of the ancient past. The deeper into space I gaze, the older the story. For us astronomers, seeing the cosmic now is impossible. The present is a luxury reserved for our local solar neighborhood. It means deep space has no universal now. Ask 2 observers moving at different speeds or sitting in different gravity wells for the time, and they will give you 2 completely different answers. Light speed anchors time strictly to the observer. Out in the deep cosmos, things just do not happen simultaneously. Everything is drifting, everything is relative to our vantage point. I find it profoundly strange. We humans love synchronized clocks. We prefer events in neat sequences, but starlight ignores what we want. It flows through the vacuum like time shifting in a dream, fluid, warped, and endlessly surprising to watch. Yet through all my years observing, the speed of light remains my most comforting cosmic constant. It never wavers. It never grows weary, it bends no rules. Whether I am sitting still or hurtling through space, I will always measure its speed as identical. It is the ultimate cosmic truth. A radiant thread binding every distant galaxy, every exoplanet, every moment. It is exactly why my night sky feels profoundly sacred. When you and I gaze upward, we are not just scanning empty space. We are reading history, a billion glowing memories twinkling quietly across the dark. Whether a photon took 3 seconds or 3 billion years to hit my telescope, it follows that exact same rule. It traveled at the identical, patient, unyielding pace. That absolute speed limit does not merely restrict my view. It connects my observatory to the farthest cosmic edge, bridging the widest voids and the most ancient epochs imaginable. It carries the tales of every star that ever burned, and tonight, some of those faint stories have found my lens. Ask most folks about the size of our solar system, and they picture bright planets strung together like beads on a wire. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, a neat planetary family orbiting the sun, each gently taking its assigned turn. But my star charts prove that charming image is false. Planets do not dominate our local neighborhood at all. The endless void dominates. Come with me, let us begin close to home. The moon orbits Earth roughly 384,000 kilometers away. That gap easily fits every single planet with room to spare. Still, it feels incredibly familiar. I can track its craters, trace its pale glow, and watch as humanity journeys there and back. Astronomically speaking, it sits right on our front porch, but our distance to the sun is about 150 million kilometers. That is roughly 400 times farther than our moon. We actually named this massive stretch 1 astronomical unit. If you drove a car sunward at 100 kilometers per hour, it would take you over 170 continuous years. Even scorching Mercury, our closest inner planet, orbits at roughly 1/3 of an astronomical unit. Venus sits at 2/3, Earth is 1, and Mars rests at 1.5. Then, the celestial bodies truly spread out. Massive Jupiter sits over 5 astronomical units away. Ringed Saturn drifts near 10. By the time my telescope finds Neptune, it is 30 units out. and between every single orbit lies a terrifying amount of nothing. If I could magically shrink our sun down to a basketball and drop it right on the 50-yard line of a stadium, Earth becomes a little peppercorn about 25 meters away. Neptune is a tiny marble sitting near the outer bleachers, and between those little specks, just empty seats. People often imagine my field of study as crowded and bustling. But it is honestly like a massive desert with one rare cactus. Most of that volume remains wide, totally silent, and deeply hollow. Even the asteroid belt, often shown as a chaotic junkyard, is truly just thousands of miles of empty space. If I stood on an asteroid out there, I would likely see absolutely nothing nearby, perhaps a faint speck afar or just endless dark. Yet Neptune is not the finale. Beyond lies the Kuiper belt, a freezing ring of cosmic debris stretching from 30 to 50 astronomical units. That is where Pluto hides, alongside dwarf planets like Ais, Halmir, and Make, tiny, freezing worlds orbiting the sun in deep twilight zones. And past the Kuiper belt, our star system just keeps reaching. Much farther into the dark, in a region so distant it feels legendary, rests the Oort cloud. I have never photographed it directly, but my colleagues and I know it exists. A giant icy shell wrapping around our entire system, stretching perhaps 100,000 astronomical units from our central star. That is over 1.5 light-years away. Let's ponder that. Our sun's gravity might reach halfway to the neighboring star, but out there, the pull is incredibly faint and time barely crawls. To truly grasp this vastness, we just have to look at the Voyager probes. I love remembering how we launched the Voyager probes in the 1970s to study the outer planets. After their main goals ended, we tracked them pushing onward. Voyager 1 sits over 150 astronomical units from the sun. It is our most distant creation. Yet as I checked the data, even after 4 decades flying at over 60,000 kilometers per hour, it still has not reached the Oort cloud. My calculations show it needs another few hundred years. And we expect it to take tens of thousands of years to cross entirely. To us astronomers, Voyager is a message in a bottle, a tiny piece of Earth sailing into the dark, holding sounds and pictures of home. It reminds me how far we have reached and what remains. Let's think about this together for a moment, all the planets. The asteroid belts, the distant comets, and our little probes still exist right in the sun's backyard. This entire solar system, for all its massive scale, is just a tiny bubble around one single star in a galaxy packed with hundreds of billions more. Sitting at my telescope, it is deeply humbling to realize that even within our own star's domain, these cosmic distances completely defy human comprehension. Yet my colleagues and I have measured them, we mapped them, we sent machines to that edge. What truly defines our solar system is not just the sun or those planets. I observe the silence in between, the waiting, the sheer loneliness, but also the constant orbital motion. Planets orbit, comets return, light streams outward. Even in empty voids I see rhythm, so how big is our system? It spans everything our teams have ever launched, everything we have discovered, and everything we still hope to reach. Looking deeper, I realize we have barely started. The sun feels so permanent. Always up in the sky, rising, setting, warming my skin, lighting the days. It feels close, so familiar. But when I point my telescope at the next nearest stars, the comforting scale of our local neighborhood vanishes. Suddenly, deep space gets very empty. Our sun's closest neighbor is Proxima Centauri. It belongs to the Alpha Centauri system, a stellar trio bound by heavy gravity. Alpha Centauri A and B are very sun-like stars. I observe Proxima Centauri as a faint red dwarf orbiting them from far away. Even as our nearest neighbor, it sits over 4 light-years off. That span, over 40 trillion kilometers, is so massive that the number almost means nothing. 4 light-years sounds easy to you and me, until we unpack what that means. Light, the fastest cosmic speed limit, takes 4 whole years for that trip. Our Voyager probe, speeding past 60,000 kilometers per hour, would take 70,000 years. That is just the closest neighbor. Let's scale down this solar system to something we can picture. If the sun were a small marble, our Earth would be a dust speck 1 meter away. Neptune sits 30 meters out. On my map here, Proxima Centauri becomes another marble over 8 kilometers away. In between, nothing but pure empty void. That makes interstellar travel an absolute nightmare. It isn't the stars themselves, it's the huge gaps. Even our top rockets struggle crossing space between simple planets. Reaching another star is a totally different game. We need propulsion systems we haven't built yet, pure energy sources we have never harnessed, and patience spanning centuries, maybe millennia. Science fiction loves jumping between stars. Warp drives, hyperspace lanes, and wormholes are all very thrilling. But in reality, we haven't sent a probe to another star system. We explore concepts like the Breakthrough Starshot Initiative, which plans to shoot tiny space probes to Alpha Centauri using powerful ground lasers. My colleagues calculate these mini probes could hit 20% the speed of light, making that trip in just over 20 years. But building, launching, and aiming something so small with flawless precision still belongs to pure future engineering. The cold truth is our universe is mostly nothing. I see stars scattered through the galaxy like distant lanterns in endless fog. Our Milky Way holds hundreds of billions. Yet the average gap between them is roughly 5 light years. Through my lens, that is a whole lot of black velvet between the light. Let's try an experiment. You and I picture a dark field stretching for kilometers everywhere. We drop one salt grain to be our sun, then we walk 8 kilometers straight out, and drop a second grain for Proxima Centauri. Keep doing this everywhere, and you will see how violently empty space actually is. A whole galaxy of tiny salt grains drifting in a massive sea of dark emptiness. But as astronomers know, those tiny grains, the actual stars, are overwhelmingly huge and powerful. Proxima Centauri is small and dim to my instruments, yet it is 130 times Earth's mass. By comparison, our Sun is over 300,000 times heavier. When I look up, I see giant roaring fusion engines burning for billions of years. Yet for all that brilliant power, they remain tiny pinpricks across a dark canvas. To us astronomers, the emptiness between them isn't just about physical space. It is about energy and time. Crossing these cosmic voids demands much more than motion. It demands survival out in the void, serious radiation shielding, and maintaining communication across decades. Upon arrival, there is no guarantee you will find anything welcoming or even solid. That is exactly why my colleagues and I study distant exoplanets so carefully. We desperately want to know if any of these faraway stars host worlds like ours. Finding another Earth orbiting Proxima Centauri or Alpha Centauri A or B would be the greatest discovery in human history. But reaching that alien world is another matter entirely. Still, despite these massive hurdles, we keep trying, we measure, we imagine, we plan. The stars may be incredibly distant, but they are never beyond our scientific curiosity. We might not reach them with rockets today, but our telescopes and minds are already there. That is the strange duality of deep space. Physically, those distant suns are untouchable. But in thought and wonder, they are intimately close, already written into our story. Perhaps that is enough for now. Knowing that out there, over 40 trillion kilometers away, another lonely star shines toward us. That its faint red light is already hitting my telescope lenses. Not in a blazing flash, but a quiet whisper, reminding us that in this vast dark, we aren't alone. You and I have probably both looked up and seen that faint milky band stretching across the dark night sky. You were catching a glimpse of something truly enormous. Our home galaxy. The Milky Way, from our observatories on Earth, it looks like a hazy smear of starlight, far too numerous and distant to resolve without a powerful lens. But that soft glowing ribbon is actually the edge of a massive spiral galaxy. A cosmic island holding hundreds of billions of stars, bound together by gravity, quietly spinning. I always picture the Milky Way as a giant flattened disk, slightly bulging in the middle. Think of a cosmic disk, roughly 100,000 light-years wide and 1,000 light-years thick. The sheer scale is something even my colleagues struggle to visualize. Even light, the fastest thing in existence, would need 100,000 years to cross from edge to edge. Tucked away inside that vast starry whirlpool is our sun, our solar system, and everything we know. We are nowhere near the center, where things get dangerously wild and densely packed. We live out in the quiet suburbs of the galaxy, about 27,000 light-years away from the core. It is quite peaceful here. our little solar system rests inside a minor branch known as the Orion Arm. We also call it the Orion Spur. It is basically a galactic side street, peacefully wedged right between two major avenues, the Sagittarius and Perseus arms. Let's picture this together. If the galaxy were a giant pinwheel, you and I are sitting midway toward the edge, steadily orbiting. It is not a terribly special spot. We have no glamorous downtown view, but it is deeply stable. That quiet stability is exactly why biological life evolved here. Yet despite resting deep in the galactic suburbs, we are absolutely not standing still. Our whole solar system is constantly moving, swept along by the Milky Way's slow rotation. Right now, our sun is tearing around the center at an astonishing 828,000 kilometers per hour. That is fast enough to orbit the Earth over 20 times in a single hour. But the galaxy is so vast that even moving that fast, one full orbit, a single galactic year, takes ages. Based on our calculations, the sun needs roughly 225 million years to finish one lap around the core. This means the last time we were in this exact region of space, dinosaurs were just starting to walk the Earth. Since our local star ignited 4 billion years ago, it has only completed about 20 laps around the center. 20 laps in over 4 billion years. It really puts the staggering size of our home galaxy into perspective. Yet despite all this incredible speed, the constellations do not noticeably shift over a single human lifetime. Looking through a telescope, the night sky looks frozen, but it is not. Everything moves, just terribly slowly on our scale. If we could run a time lapse spanning millions of years, we would watch stars swirl like fireflies in a slow, graceful dance, mapping the galaxy's spiral arms. But the center of the Milky Way is wildly different from our quiet home. Down there, stars are packed tightly, orbiting a terrifyingly dense object, a supermassive black hole we astronomers call Sagittarius A star. It weighs as much as 4 million suns, sitting like a quiet anchor at the galactic core. You and I can never see it directly, but we watch it whip nearby stars into breathtaking, violent orbits. For us astronomers, the Orion Arm is a beautifully quiet neighborhood. Stars sit farther apart. When I study these regions, I see plenty of space for planets to orbit safely, letting life slowly emerge over billions of years. I often think we simply lucked out with our cosmic real estate. The truly amazing part, when you and I look up without a telescope, everything visible in that night sky. Every single star you have ever wished on sits within a few thousand light years of Earth. That is just a tiny fraction of our Milky Way galaxy. As an astronomer, I know most of our galaxy hides in the dark, obscured by immense distance, thick cosmic dust, or simply too faint. Yet our instruments prove it's there. By running radio antennas and infrared surveys, my colleagues and I map those spiral arms, track star movements, and uncover the ghostly dark matter halo wrapping around everything. It is incredibly easy to treat our galaxy as a simple, pretty backdrop during a stargazing session, but my research shows it is so much more. The Milky Way is our personal island in this massive cosmic ocean. It is the only star system I can study from the inside, everything humanity has ever done. Every civilization, every idea, every sunrise, and every song happened on a tiny rock, orbiting a sun that quietly circles a galaxy my field barely fully understands. And we keep moving, still riding that giant spiral, still drifting around the galactic core like leaves on a quiet stream. No matter how peaceful my observatory feels, we are flying through space at hundreds of thousands of kilometers per hour. It is a journey spanning billions of years with no end in sight. That is our place in this galaxy. We are not the center, not truly special, but not meaningless. Just one piece of an ancient, beautiful structure slowly spinning in the dark. Looking through the eyepiece, it is easy to imagine that stars are just thrown randomly across the deep void of space, each shining totally alone, but astrophysics tells us a different story. Stars usually form together in large families, born from the same gas clouds, locked together by gravity and a shared birth. These beautiful stellar gatherings take many shapes, and each gives me a unique story about stellar life cycles and the physical architecture of our home galaxy. Let's observe the open clusters together. I see these as loose collections of stars, maybe a few hundred to a few thousand, all born inside one giant molecular cloud. They are quite young, astronomically speaking, often just a few million to a billion years old. Because they have not had enough time to drift far away, my observations show these members remain loosely held by gravity. I like to call open clusters stellar nurseries, freshly out of the cradle. The Pleiades, or the Seven Sisters, is a classic example. On a perfect night, even without my telescope, you can easily spot them as a tight, glowing cluster of stars parked right inside the constellation Taurus. The Pleiades are roughly 100 million years old. To an astronomer, they are absolute infants, still glowing with a very hot, youthful blue light. They serve as a stunning reminder that suns are usually born in batches, never completely alone. Next, we have the globular clusters. Entirely different beasts. I study these dense, spherical collections of stars, which often pack together hundreds of thousands or even millions of suns. Unlike the open ones, globular clusters are incredibly old. Spectroscopic data shows some are 12 billion years old, nearly matching the galaxy's own age. Through our lenses, we watch them orbit the Milky Way in a massive halo outside the main disk, just like glowing bees swarming a hive. These clusters are jammed so tight with aging stars crammed so close together that a single exposure from my telescope easily captures thousands of distinct light points, all burning in one compact ball. One of my favorites is M13, the Great Hercules Cluster. It sits roughly 25,000 light-years away and holds over 300,000 stars. If we could stand on a planet deep inside that cluster, our night sky would be completely blazing with intense starlight. Infinitely brighter and vastly more crowded than anything I ever see from Earth. And beyond the star clusters, I study the nebulae. Those beautiful, hazy clouds scattered across the galaxy. In astronomy, the term nebula traces back to the Latin word for cloud, which fits perfectly. I observe them as giant walls of gas and dust, often spanning hundreds of light years. They provide the raw cosmic material to birth new suns, and occasionally they are the expanding ghosts of stars that already died. The Orion Nebula is definitely the most iconic. I can easily spot it just below Orion's belt in the winter sky, even with a basic amateur telescope. Sitting roughly 1,300 light-years out, it belongs to a much larger astrophysics hotspot called the Orion Molecular Cloud Complex. Right now, my thermal cameras show brand new stars igniting inside that nebula. They aggressively heat the surrounding gas into a glowing storm of red, blue, and purple. As astronomers, it is our closest and most heavily analyzed stellar nursery. A quiet laboratory where the next generation of suns flickers into existence. Then we have the Eagle Nebula, holding the legendary pillars of creation. Those towering gas columns are breathtaking. The Hubble Space Telescope gave us all a truly unforgettable image of them. You and I are looking at massive structures tonight. These pillars stand several light-years tall, serving as quiet cradles of star birth. Deep inside, dense knots of gas collapse under gravity. They are forming brand new stars, completely hidden from our telescopes by thick, dusty clouds. What constantly humbles me at the observatory is how tiny these magnificent formations actually are on a galactic scale. A standard nebula might stretch across a few dozen light-years, a giant one maybe a few hundred. Yet the Milky Way spans 100,000 light-years across. That makes a sprawling stellar nursery like Orion or Carina. Packed with glowing gas and brilliant colors, just a tiny smudge on our maps, a simple dust mote trapped in a spiral arm. Even the largest star clusters become just simple dots of light when we look from far enough away. They might hold millions of blazing suns, but they practically vanish compared to the sheer, dark vastness of our galaxy. If our galaxy was a giant canvas, these bright clusters and nebulae would just be delicate, glowing brush strokes. Little flourishes you would barely notice from afar, yet inside those tiny strokes, beautiful cosmic dramas play out. Suns ignite, burn for billions of years, and die in spectacular blasts. Worlds take shape from the leftover dust and rock. Moons crash together and reform. Life itself might wake up on some quiet ocean planet orbiting a young star. It humbles me to know that every speck of light I log, every single dot in a cluster or bright swirl in a nebula, could be hiding deep histories we can barely even imagine. These stellar neighborhoods are so much more than random stars. They are sculpted by intense gravity, deep time, and strict physical laws. Stars born in the same cloud might slowly drift apart, pulled by galactic tides, but while they stay close, they share far more than empty space. They share identical chemistry, age, and motion, a true cosmic family. My colleagues and I study these groups to understand stellar evolution by watching stars at different life stages. But with the exact same age and makeup, we piece together how these massive bodies grow, shift, and finally die. Analyzing the light from nebulae lets us map the raw ingredients of star formation, tracking the very elements that build planets, dark oceans, and ourselves. These little star clusters, scattered across our galaxy like silver dust on black velvet, are easily my favorite sights through the telescope. They are the exact zones where suns are born, where they gather and fade away. Just quiet cosmic blocks in a galaxy that never rests. They might just be tiny smudges on the Milky Way map, but this is exactly where the story begins. Inside the faint glow of a nebula or a packed cluster core, the universe is quietly writing its next chapter, single star by single star. For decades, my predecessors stared up into the dark night and honestly believed they were seeing it all. Just stars, planets, maybe some thin clouds of gas, and the rare fuzzy patch we logged as a distant nebula. The Milky Way arching overhead felt like the absolute edge of reality, but with larger lenses and endless patience, our field stumbled on something mind-bending. We were missing almost the entire picture, not even close. Let's look at one of the boldest moves in astronomy. In the mid-90s, we aimed the Hubble telescope directly at an empty, boring patch of sky. No bright stars, no famous constellation in sight. Just a pitch-black corner of deep space, roughly the size of a grain of sand held at arm's length, and Hubble just stared. For over 10 straight days, it captured faint photons from that silent void. Most scientists expected a completely blank image. The actual result rewrote our entire understanding of space. The data returned as the legendary Hubble Deep Field. Instead of a black void, we saw a frame overflowing with light. Thousands of distinct galaxies, every single one packed with stars. Beautiful spirals, tight ellipticals, weird smudges, burning cores, and long arms. They flooded the exposure like dust in a sunbeam. Those were not local stars or planets, they were whole galaxies holding billions of foreign suns. Each one floating impossibly far from Earth. Keep in mind, this was just one tiny speck of the night sky, a total fraction. If a single deep field image captured thousands of distant galaxies, just think about how many are hiding across the rest of the cosmos. That massive question forced my colleagues to run the numbers. We scaled up what we saw in that tiny window, running the math based on dozens of similar deep field observations. The final result, an estimated 2 trillion separate galaxies floating out there in the observable universe. 2 trillion giant islands of stars, complete with their own planets, gas clouds, heavy black holes, and secrets. Now here comes the real twist. Most of those star cities remain entirely invisible to our lenses. Even using our biggest telescopes, the ancient light is either too incredibly faint, stretched out by cosmic expansion, or totally blocked by heavy dust. You and I share a universe full of hidden wonders. They are definitely out there, waiting for our eyes and instruments to finally catch up. As an astronomer, looking up feels like trying to understand the ocean from a single drop. There is depth, movement, and life. But it is just a tiny sample of a vaster cosmos. The exact same principle applies to galaxies. Through our telescopes, we only catch a fraction of what exists. Yet, the fact that I can observe anything at all feels like magic. These deep space objects are impossibly distant. Some of the starlight hitting my lens began traveling billions of years ago. It has traveled across the expanding void of space, stretched into longer, redder wavelengths as the universe swelled, finally arriving at our small planet, filtering down into the very space telescopes my colleagues and I put into orbit. Let's pause and think about that for a moment. Every star system I study in those deep field images isn't just distant, it's ancient. I am observing them as they were, not as they are. Many might be completely gone. They might have collided, merged, burned out, or completely transformed. But their ancient light is still crossing the dark, whispering their history to astronomers who listen. and that is merely the observable edge of our universe. The region of the cosmos where light had enough time to reach my instruments since the Big Bang. There could be so much more beyond our horizon. A whole lot more, massive regions of space too distant for their light to arrive, or perhaps forever lost to us because of the universe's accelerating expansion. Which leaves me with a very humbling question. Are we surrounded by galaxies I will never get to observe? The answer is likely yes. The cosmos is expanding, and not just in the normal sense of objects drifting apart. The actual fabric of space is stretching out, carrying galaxies along like raisins inside baking bread, and the further out I look, the faster those objects seem to speed away. Past a certain point, roughly 14 billion light-years out, that retreat becomes faster than light itself. Not because the distant galaxies are zooming away, but because the emptiness between my telescope and them is growing. This means plenty of galaxies are already completely unreachable today. Their fading light will never hit our lenses, no matter how patiently I wait. They have slipped past the cosmic event horizon. It feels like the universe is quietly closing the curtains on itself. Still, even inside our observable bubble, the sheer number of star systems is absolutely staggering. Every single one has unique structures, its own stellar populations, and countless orbiting alien worlds. Some appear small and faint, holding only a few billion stars. Others are massive, glowing giants with hundreds of billions of suns, illuminating their beautiful spiral arms and elliptical shapes. Even with a math background, I struggle with these numbers. 2 trillion galaxies, each packing hundreds of billions of stars. Do the math and we get roughly 200 sextillion stars. That is a 2 followed by 23 zeros. And that completely ignores the stars my sensors cannot detect yet, or the ancient ones that already went dark. And yet step outside the observatory without a telescope, and you and I can spot only a few thousand stars with the naked eye. 0 galaxies, except Andromeda's faint smudge and maybe the Magellanic Clouds down south. The rest stay hidden, locked behind an endless veil of distance and deep night. I find it almost comical. We inhabit a universe stuffed with galaxies, yet to my eyes, most remain totally invisible, unreachable, and unknowable. We drift in a vast cosmic ocean surrounded by glowing islands, only able to study the nearest waves. I find a certain beauty in that limit. Every single galaxy we do capture becomes deeply precious. A single deep field exposure becomes a massive cathedral of starlight. A stark reminder of what is out there and how little we need to feel pure wonder. I know we will never observe them all. I might never map every distant spiral or track down the faintest glimmers from the edge of time, but I can imagine them. I know they exist. For me, that scientific knowledge alone is enough to stir something very deep inside. Because somewhere way beyond the limits of my largest telescope, another galaxy spins quietly in the dark. Even if its starlight never finds my lens, it still shines. You and I usually think of a neighborhood as a few local houses, maybe 2 streets over. A small community we could walk across on a lazy night. But in my field, our cosmic neighborhood, the local group, means something entirely different. It is a massive gravitational family of galaxies stretching millions of light years across, bound loosely together by the quiet, steady pull of gravity. We map about 50 galaxies in the local group, though the math shifts depending on how my peers define a galaxy and if we count the absolute faintest ones. Most of these are not massive spirals or glowing giants. I usually see small, irregular dwarf galaxies, dim clusters of stars orbiting bigger neighbors just like tiny moons. But my data shows a few standouts, with 2 major heavyweights dominating our local group. Let's look through the lens together at our Milky Way and the Andromeda Galaxy. Our home is massive, holding 200 to 400 billion stars. But Andromeda, which we call M31, is even larger. It's the heavyweight of our local group, packing around 1 trillion stars in a sharp spiral. At 2 million light-years away, my colleagues and I consider it right next door. I often tell people you can spot it under dark skies without a telescope, just a faint, hazy smudge. It always gives me chills to realize that when I observe it. I am catching starlight that has been traveling across the void for over 2 million years. What really keeps me up at night is knowing this quiet, blurry shape is heading straight for us. That's right. Our Milky Way and Andromeda are drifting closer, locked in a slow, mutual gravitational pull. Even as the cosmos expands, local gravity wins out. I track our two spiral galaxies closing the gap at roughly 110 kilometers per second. In roughly 4 billion years, they will collide. You and I might picture a violent crash, but galaxies are mostly empty space. When they merge, the stars won't actually hit each other. They will simply pass through one another like ghosts, guided by gravity. Gradually, their beautiful shapes will warp and their star fields will mix, leaving behind a giant elliptical galaxy we sometimes call Milkomeda, a fun blend of their names. It will be an entirely new kind of home. For now, our telescopes show both galaxies completely separate, each hosting smaller satellite galaxies. The Milky Way alone anchors dozens. The most famous are the large and small Magellanic Clouds, irregular dwarf galaxies I've often admired from the southern hemisphere. They trace loose, looping orbits around us, and they are among the rare star systems you can spot without gear. I also track the Sagittarius dwarf galaxy, which our Milky Way is currently tearing apart and absorbing right now. The massive gravity of our host galaxy pulls and warps these smaller companions, stretching their stars into long rivers that wrap around the galactic disk. I like to call it cosmic recycling. We grow by eating our neighbors. Andromeda has its own captured satellites too. In my observations, galaxies like M32 and M110 orbit near its spiral arms. Eventually, Andromeda will consume some of these entirely, feeding even more stars into its already massive, swirling population. As an astronomer, I see these gravitational bonds shaping the whole local group. It isn't a tightly packed cluster like we observe in more crowded regions of the deeper universe. Our local galaxies sit far apart across vast, dark stretches, yet my data shows them linked, gracefully orbiting a shared center of mass like slow dancers circling nowhere. Out between these galaxies sits the intergalactic medium, a faint fog of thin gas and dark matter stretching across the void. My instruments cannot see most of this directly, but I can clearly measure its heavy gravitational pull. This hidden web of mass is what controls our local group, steering these galaxies as they slowly drift and mingle over deep time. My colleagues and I believe our neighborhood belongs to an even bigger structure, the Virgo supercluster, which itself is just a tiny thread in an impossibly grand cosmic web we call Laniakea. But here in our little pocket of space, things stay pretty calm. I don't see any massive galactic pileups happening right now. Just slow, steady movement. I watch an ancient gravitational ballet unfold across millions of light years. The trickiest part of studying the local group is that its tiny dwarf galaxies love to hide from my lenses. They are incredibly faint, low in mass, and blend into the dark background. A few only hold a couple million stars, which is microscopic for a galaxy. I usually only find them by staring at star movements or catching tiny, subtle dips in brightness. As our observatory gear gets sharper, my team keeps uncovering hidden new neighbors out there in the dark. It fascinates me to realize that these little, dim star clusters might secretly run the whole show. As an astronomer, I suspect these small dwarf galaxies are the core building blocks for the giants. I believe the Milky Way and Andromeda only grew this massive by eating these tiny star clusters. When I study their dark matter, star ages, and chemistry, I am looking for the missing pieces to how galaxies form. Looking through the eyepiece humbles me, knowing these galaxies are deeply ancient. They've been floating out here for billions of years, slowly changing, sometimes crashing, mostly just sitting in perfect silence. Long before Earth ever formed. This whole local group was already moving, and long after we are gone, I know these stars will keep orbiting, merging, and glowing quietly in the dark. When you and I picture the universe, it's tempting to focus on the largest structures, all those infinite galaxy clusters and dark webs, but as an astronomer, I find true peace just studying our own quiet corner. Let's look up together. This local group is just one cosmic family out there, but it is ours. We observe it from within, around 50 galaxies, 2 massive spirals. Dozens of dwarf galaxies, countless stars drifting slowly through the dark. Through my telescope, it feels less like a city and more like a quiet village, each galaxy drifting by gravity's slow, patient pull. Not crowded, not empty, just enough to remind us we are not alone in deep space. When we observe the night sky, we see more than mere points of light. We are witnessing a much grander structure, a massive celestial community. A neighborhood of ancient star systems, each holding old secrets. If single galaxies are cities, then galaxy superclusters are continents. Huge expanses of the cosmos holding far more than just a few galaxies. We map tens of thousands of them, organized into massive clusters linked by delicate dark matter threads. My colleagues and I do not see random stars, we find structure, deep patterns. These patterns remain the most majestic designs in all of astrophysics. Our Milky Way and its local companions actually belong to a far more massive cosmic system. The Laniakea supercluster, a Hawaiian name that translates beautifully to immense heaven. A perfect title, really. Our measurements show it spanning 500 million light-years, holding over 100,000 galaxies. Even as an astronomer, grasping that scale is difficult. 500 million light-years, a photon would need 500 million years to cross it. Yet Laniakea is not an isolated island in space. It is simply one node in a web spanning the entire observable universe. We call it the cosmic web, a massive network of gas, dark matter, and gravity. When my team runs supercomputer simulations of this large-scale structure, it looks like a glowing spider web. Dense galaxy clusters sit at the busy intersections, while long gas filaments connect them like glowing bridges. Between these bridges lie massive voids, pockets of deep space holding almost nothing. They are profoundly empty. Stretching hundreds of millions of light years, they are entirely barren, pure black ink between bright strokes of paint. Silent cosmic deserts surrounded by glowing cities. But as an astronomer, I know these voids actually shape universal evolution. Their sheer emptiness dictates exactly where matter decides to gather. This grand cosmic web had an origin. It started as tiny matter density ripples right after the Big Bang. Across billions of years, gravity slowly magnified those tiny differences. Denser pockets pulled in more dust, forming clusters, while the thinner spaces simply expanded into massive dark voids. The final result is a night sky sculpted entirely by gravity and deep time. Looking at the data, these patterns look exactly like fractals. Complex geometry repeating at different scales. Focus the lens, you see galaxy clusters. Zoom out, they become giant superclusters. Zoom out again, and those connect via long filaments, reaching the very limits of our observations. Each scale mirrors the last, not perfectly identical, but with a poetic structural rhythm. Space repeats its grand designs, from individual stars up to vast galaxy networks stretching across billions of light years. 2003. We discovered the Sloan Great Wall. It is absolutely massive, 1.3 billion light-years wide, holding multiple galaxy superclusters bound tightly together. Finding the Hercules Corona Borealis Great Wall truly shocked our observatory team, revealing formations so immense they completely challenge our modern cosmological models. And yet, all this is just the fraction of space we can observe. I often wonder about what lies beyond our telescopes, cosmic regions whose faint light simply hasn't reached Earth yet. This web could be truly infinite, or perhaps it forms an even stranger pattern we haven't decoded. Sitting at my desk, these scales feel impossible. We live on one small planet, orbiting a single star, surrounded by billions more in the Milky Way. Our home galaxy sits in a small group, tucked inside Laniakea, which is just a single fragment of the cosmic web, woven across deep space like an ancient, expanding fabric. Think about this with me. We mapped this network using starlight that is literally billions of years old. By measuring the redshift of millions of distant galaxies. In my field, we've built three-dimensional maps of cosmic structure. Come with me. Let's trace where these galaxies cluster, string into long filaments, and where the deep dark patches lie. In my work, it feels like photographing the skeleton of the universe. The glowing stuff, stars, gas, galaxies, traces out the hidden shape of something far bigger, something completely invisible. Because most of the mass out there simply doesn't shine. We call it dark matter. It won't emit or absorb light, but its heavy gravitational pull gives it away. My maps of the cosmic web show this dark matter first and ordinary dust second. Through our telescopes, we see the scaffolding of the universe. When I zoom the data out far enough, sharp details fade. Individual galaxies blur together into a haze. Clusters become tiny dots and filaments stretch thin. Eventually, my instruments hit a limit, not just a drop in resolution, but a shift in meaning. At a certain scale, the universe becomes statistically uniform. No more tangled webs or structures, just a very smooth, endless field of evenly spread energy and matter. As a cosmologist, I call this the cosmological principle. On the grandest scales, deep space looks exactly the same in every possible direction. Not a blank, featureless void, but a deeply balanced whole. Still, sitting at my desk, it feels humbling. We occupy a tiny galactic suburb in this massive cosmic web, stretching across the dark void like veins pulsing inside a living organism. A living universe with texture and flow. A quiet place where gravity and time draw invisible lines, guiding swirling galaxies over billions of years. Yet, even as an astronomer, I am no outside observer. We are deep inside it, woven right into the web. Every atom in your body was once burning inside a star. And every star belongs to a galaxy. Each galaxy glides along the heavy threads of this cosmic structure, pushed and pulled by ancient gravitational forces set into motion at the dawn of time. You are, in a very real sense, physically connected to everything, to the stars in distant galaxies, to the faint light from ancient times, and to the massive cosmic architecture humming quietly just beneath the surface of our night sky. Looking at my supercluster maps, it is so easy to feel small. But maybe it feels better to just feel included, to realize we belong to something enormous, not as outsiders peeking through a lens, but as vital pieces of a grand, unfolding pattern. I can zoom my models out until the universe blurs, but right before it fades away, it reveals something truly profound to me. A hidden order, incredibly delicate and vast, stitched perfectly across time and deep space. A giant structure telling a story much older than any single galaxy, yet it is a story we belong to. As far as my telescope can see, the universe doesn't come with walls. There is no giant stop sign out at the edge of space, no heavy dark curtain we can pull back to see what lies behind. But you and I both know there's a limit to what we can observe, not a physical wall in space, but a hard limit in time. A horizon drawn not by what exists, but by what ancient light has finally had time to reach my lenses. We call this sphere the observable universe, stretching about 93 billion light-years across. That is an unimaginably massive number, truly staggering. But that isn't the total size of the universe, just the small pocket my telescopes can actually see. Just like standing on a dark mountaintop looking at the horizon, my visible cosmic edge is defined not by what is physically there, but by what falls within reach. To understand why an astronomer faces this limit, we must think about light. Starlight does not travel instantly. It takes real time to cross deep space. Since the cosmos is roughly 13.8 billion years old, you might assume my telescopes can only see 13.8 billion light years away. That makes perfect sense, assuming space wasn't expanding. But cosmic space is expanding. It has been stretching since the Big Bang, and I assure you, not in a gentle, relaxing sort of way. The expansion is actually accelerating. This means the faint light I capture from distant galaxies was emitted eons ago when they sat much closer. As that light made its long trek toward Earth, space stretched out, dragging those ancient light waves along with it. By the time they hit my lens, those galaxies had drifted even farther away. Because of this massive cosmic stretching, the photons from my most distant visible objects come from galaxies now over 46 billion light-years out. Double that distance and you get our observable universe's full diameter, roughly 93 billion light-years across, give or take a few 100 million in my calculations. So while the cosmos is 13.8 billion years old, the bubble I can actually observe is vastly larger. Picture shining a flashlight beam across a rapidly inflating balloon. Except the beam stretches, the rubber surface expands beneath it, and by the time light arrives, everything has violently moved apart. Stick with me here, I know it sounds completely mind-bending. Human brains are great at tossing apples, climbing ladders, and reading traffic lights, but terrible at visualizing space bending and stretching like warm taffy. But my math checks out, and the observatory telescopes confirm it all. I can photograph galaxies whose light began traveling billions of years ago, long before Earth even formed. Some of these ancient galaxies are so faint and redshifted on my screens, they are barely detectable. Through the telescope, they appear as faint smudges, ancient ghosts hovering at the edge of my vision. But past those galaxies lies pure darkness, not because deep space is empty, but because their starlight hasn't had time to reach my instruments, and honestly, it never might. This is one of the strangest truths you and I face in an expanding cosmos. There are pockets of deep space that we will simply never observe, no matter how many nights I spend looking. The light is just too far gone. Cosmic expansion is too fast. They sit beyond the cosmological event horizon. That's the hard limit where no signal can ever reach my screens, not even at light speed. But that doesn't mean those distant regions are empty. Actually, they might be overflowing with ancient galaxies, brilliant stars, and hidden civilizations. But to an astronomer like me, they remain forever invisible, locked behind the dark, heavy curtain of cosmic acceleration. People often think it's strange that our observable universe revolves around Earth, but we aren't special. It surrounds us simply because my telescope is parked right here on this planet. An alien astronomer in another galaxy would map out their own visible cosmos, roughly 93 billion light-years wide, perfectly centered right on their own observatory. While our star maps might overlap, the distant outer edges would look completely different. Every single galaxy, every quiet planet, every dark patch of sky holds its own personal window into the cosmos. When my colleagues and I talk about the observable universe, we aren't picturing some rigid box floating in space. We mean a massive sphere of visibility. It's our ultimate field of view, carved out by the age of light and the strict rules of relativity. Within that sphere I see plenty, massive galaxies strung together in thick clusters and glowing filaments. Supernovas flashing from the deep past, brilliant quasars roaring from the dark cores of infant galaxies. I can even track the fading afterglow of the Big Bang itself, that cosmic microwave background radiation arriving from a cold era just 380,000 years after everything started. That ancient light has traveled ever since, bringing me the frozen fingerprints of the earliest cosmic structures. But every telescope has its limits. Past a certain invisible line, ancient galaxies grow far too distant and impossibly faint for me to catch. Their light is redshifted off my monitors. Some hide behind thick clouds of cold intergalactic dust. Others are walled off simply by the age of the cosmos. They just haven't had enough time to shine their light down into my observatory. Then you and I face the real philosophical questions. If my lenses can't see it, does it count? Is that unobservable dark space just as real as the stars I map every night? My colleagues and I believe so. Physics doesn't just magically break down past my telescope's line of sight. Space almost certainly marches on past that dark horizon. It could truly be infinite. It might loop back on itself or bleed into something totally unknown. But for tonight, I just have to work with the light I can actually catch. 93 billion light-years of hard data, spinning into a massive, glowing, expanding web of ancient stars and galaxies. It is more than enough to keep an astronomer busy, but here is a comforting thought. Inside this little bubble, we have decoded so much. We have mapped the galaxy clusters, measured the steady expansion rate of deep space, carefully weighed the silent dark matter and dark energy, and pieced together the very first blazing moments of cosmic history. We have launched giant mirrors into orbit, stared into the blackest voids, and trapped ancient light that began moving long before Earth even existed. Even if my visible universe is just a tiny sliver of the whole, it is a truly breathtaking sliver. It holds the quiet fingerprints of deep time, the faint echoes of dead stars, and the grand blueprint of everything humanity knows. Past that edge, there might be so much more, strange regions running on different physics, maybe even silent copies of the Milky Way. Maybe things so bizarre my instruments wouldn't even register them. But whatever rests beyond my observable edge, it stays quietly locked away behind the simple, brutal barrier of time. And that is the true, quiet wonder of the observable universe. I am not staring at the end of reality, just the absolute edge of my sight, a softly glowing horizon, constantly backing away, forever out of my grasp. It is not a limit on creation. It is just a reminder of how far light travels and how deep we have reached to catch it. I observe a vast cosmic horizon surrounding Earth. It isn't built from walls or gas, but forged from time and light. It's just a gentle boundary where the furthest starlight simply hasn't had the time to hit my lens yet. In my field, that dark boundary defines the observable universe. A sphere spanning 46 billion light-years outward, but you and I must ask, what hides beyond it? That exact question drags astronomers right into the deepest, darkest mysteries. Because if my telescopes can only ever process the light that has physically managed to reach Earth, then the vast remainder of space, the unobservable hidden universe, could be massive beyond human comprehension, and my instruments will simply never see it. My search starts in the very earliest moments of time. Right after the Big Bang, inside the first fraction of a second, space slammed through a violent phase I study called cosmic inflation. The math shows this wasn't some gentle swelling or a quiet breeze through the young void. It was an absolute explosion of space, unimaginably fast and completely, mind-bendingly brief. You and I are looking back to a fraction of a second when space expanded faster than light. It stretched tiny quantum ripples into massive structures that eventually formed our galaxies and stars. As an astronomer, cosmic inflation solves our biggest headaches. It explains why the expanding universe looks so beautifully smooth through our telescopes and why space appears perfectly flat instead of curved. It also planted the seeds of the vast cosmic web I observe every night. Those ancient ripples, frozen by inflation, literally became the blueprint for everything out there. Gravity gently pulled matter together, and over billions of years, stars ignited right where those ancient echoes drifted. As things finally cooled off about 380,000 years after the Big Bang, early light broke free. We were left with a remarkably soft, warm afterglow. That gentle glow still surrounds us today. We astronomers call it the cosmic microwave background, or CMB. It is the absolute oldest light our instruments can detect, but not the oldest thing in existence. It is simply the oldest light that has finally reached our lenses, and that brings my focus right back to the cosmic horizon. Everything resting beyond that faint glow, farther than that ancient light, hides in total darkness. Not because it is entirely empty, but because its light hasn't reached my observatory yet, and with space constantly stretching, some of those faint messages will simply never arrive. They sit too far away, the void between us expands too rapidly. Starlight is racing toward my telescope, but the cosmos is stretching faster than the beam can travel. It feels just like standing on a dark shore, watching a ship vanish. I know deep ocean is out there, but I simply cannot see it. No matter how hard I stare, the vessel stays perfectly hidden. Not because it faded away, but because the light it casts will never reach Earth. So, what exactly is lurking out there? What truly lies past our cosmic horizon? The easiest answer in my field is that the universe simply continues on, just like our local neighborhood. More galaxies. More sparkling stars, massive clusters, and deep voids. A beautiful, endless quilt of matter stretching everywhere. If the laws of physics hold up everywhere, there is truly no scientific reason to believe our little patch of sky is special. The unobservable universe might be terrifyingly huge, but still deeply familiar. In fact, many of my colleagues believe the universe is either impossibly vast or completely infinite. If that holds true, then our observable universe is just a lonely bubble floating in an ocean of space, one tiny patch of a much larger whole. I could theoretically fly a ship in a straight line forever and never hit a boundary. No edge at all, just endless, quiet space. In a model like that, every single possibility allowed by physics happens out there somewhere. We might even find distant sectors where matter arranged itself exactly like our solar system. Not through magic or parallel dimensions, but because with enough infinite room, repetition becomes pure mathematical certainty. My math even suggests that statistically, an identical twin to our universe sits roughly 10 to the power of 118 meters away. That is a one followed by a number so massive, we scientists rarely even bother writing it. Naturally, that doesn't mean we can actually reach those distant places. Even if the cosmos never ends, the vast majority of it stays permanently out of our grasp. Let's think about this together. Space is expanding so fast that countless galaxies have already slipped over the horizon. Their beautiful light is completely lost. Their ancient histories, their brilliant stars, and any alien civilizations are effectively erased from our starry future. It feels a bit like working inside a dark snow globe. I can sit here and map the glittering flakes of our local nearby galaxies. My team measures their distances, traces their cosmic drift, and peers straight backward through time. But outside that glass dome, everything blurs, not because it is empty, but because the photons just haven't hit my lens yet. And out past that very same glass, we might find places where physics itself completely changes the rules. Some inflation models I study suggest our own universe is just a single pocket among thousands, a fragile bubble drifting through a vast multiverse. In this theory, those neighboring bubbles might hold entirely different physical constants. Bizarre new particles or completely different spatial dimensions. Many would be completely dead and inhospitable. Others might prove far stranger than any astronomer could dream. If inflation kicked off once, it could happen again and again, churning into an endless foam of universes. But here is the frustrating part for us. My equations are mathematically flawless, but they remain almost impossible to test. By definition, the unobservable universe stays completely outside our instruments. I can make educated calculations based on theory and faint radiation, but my colleagues and I may never pull a solid answer. It feels like hearing a strange noise behind a heavy locked door, desperately trying to map out the room. I can publish highly plausible theories, but until that cosmic door swings open, they remain nothing but educated guesses. But you and I can find comfort in that uncertainty. It reminds us astronomers of our optical limits and brings real humility to our place in the cosmos. We have come a remarkably long way in astrophysics, tracing everything from the roaring Big Bang down to the heavy, sprawling galaxy clusters floating above us today. Yet my telescopes will always fall short. There is always more out there, stretching quietly into deep darkness. Maybe that is the beauty of our work. For you and me, the cosmos isn't a puzzle to solve, but a deep mystery we simply live alongside. A celestial story that fades into silence. For us astronomers, the unobservable universe is not a flaw in our understanding. It is a feature of deep space, a vast, unknowable expanse waiting just past the edge of the light we can capture. Though my telescopes cannot see it, we remain part of it. We are forged from the same stardust, bound by the same laws of physics, drifting through this shared spatial ocean. We will always stay curious. We will always wonder. It makes us explorers. And even if my lenses never pierce that final horizon, it will never stop me from looking up. Sweeping the heavens for faint radio signals, ancient echoes, and distant starlight whispering from just past the edge of our vision. When I look through the eyepiece, it is easy to picture galaxies as objects floating in a void, just cosmic ships sailing across a dark ocean. That is exactly how it feels when I study our deep space photographs. Galaxy clusters drifting apart, spiral arms spinning quietly, caught in a slow cosmic ballet. But for us astrophysicists, that beautiful picture is not entirely correct. Galaxies are not just moving through the void. What the data shows is far stranger. Space itself is stretching. This stretching of the vacuum is one of the most counterintuitive, yet breathtaking ideas we study in modern cosmology. It means these massive star systems are not plowing through some static, pre-existing emptiness. Instead, the very fabric of the vacuum between them grows. These galaxies are carried apart, not by their own engines, but by the swelling of the cosmos around them. They are not swimming through water. They are resting in the water, and the water itself is rising. As an astronomer, this story begins for me with a 20th century giant, Edwin Hubble. In the 1920s, Hubble was tracking galaxies through the 100-inch telescope at Mount Wilson Observatory in California. Back in those days, my predecessors were just realizing that the faint, fuzzy patches on our photographic plates were not just gas clouds inside our own Milky Way. They were massive, independent galaxies, holding billions of stars, sitting unimaginably far away. Hubble measured the light spectra from these objects and caught something strange. The light waves were stretched, pushed entirely toward the red end of the spectrum. This redshift was no mere instrument error. It showed up consistently, increasing with every distance. The more distant the galaxy, the redder its signature. This was a massive clue for us. When light waves stretch like that, the source is usually moving away. Think about the Doppler effect with me for a second, like how a passing car drops in pitch as it speeds away. The exact same physics applies to starlight. If a galaxy races away from my telescope, its light becomes stretched, reddened, and elongated. But Hubble found more than random motion. He plotted a clear pattern. The further out a galaxy sat, the faster it appeared to fly away. We now call this relationship Hubble's law. It gave the scientific community its first rock-solid proof that the entire universe is expanding. Yet again, this was not standard motion. Over the decades, my field realized these galaxies were not just exploding outward like sparks from a firework. The actual space between them was growing. The star clusters were mostly sitting still, just like raisins inside a loaf of baking bread. The raisins do not crawl around, but the dough expanding between them forces them miles apart. This expansion model became a core pillar of modern astrophysics, leading to some truly strange realities. For one, it guarantees that over eons, galaxies will drift further and further apart. Not because they have their own momentum, but because our universe just keeps stretching. And that expansion is only speeding up. We call the mysterious driver of this acceleration dark energy, and it forces the cosmic fabric to stretch faster and faster. My colleagues and I cannot fully explain dark energy, but we track its gravity. Galaxies that were once faint smudges on our monitors are now vanishing beyond visibility. The light they shine gets stretched so violently it fades to black, redshifted far beyond what our most sensitive sensors can detect. Eons from now, entire star systems will slip quietly past our cosmic event horizon. Their ancient light will never reach my lenses again. They will physically exist, but to an observer on Earth, they will completely vanish. Not because they traveled away, but because the void between us grew too wide, too fast. For an astronomer, this leaves a sobering thought. Right now, you and I can see millions of galaxies shining across the night sky. But as the cosmos keeps aggressively expanding, the vast majority of those targets will fade away. Billions of years from now, a future astronomer standing in whatever remains of the Milky Way might point their telescope up and find just a handful of local neighbors. The rest will be gone, their signals lost forever. It is a quiet, strange fate. Our universe was born as a superheated, dense soup of primeval particles, crushed tightly together. Then it expanded, cooled, and formed the galaxies, stars, and planets I study today. Now it stretches so quickly that most of these distant galaxies will slowly fade from our telescopes entirely. The cosmos is slowly pulling itself apart, not with violence, but with a quiet, undeniable certainty. Yet for me, the real beauty isn't just the sheer scale. It's how my colleagues and I found out. We spent nights in quiet mountaintop domes and launched massive telescopes into orbit, just tracking light. You and I are learning that as the universe expands, our grasp of it grows too. But this stretching doesn't treat every region of deep space the same. Home galaxies like our own Milky Way are gripped by gravity. The stars inside stay bound together because their gravitational pull easily overpowers that outward cosmic stretch. Even neighboring celestial bodies, like Andromeda in our galaxy, hold onto each other tightly enough to fight off the dark energy pulling them apart. Actually, my charts show we will crash into Andromeda in about 4 billion years, so you would never notice this expansion just by looking at our local neighborhood. You only see the stretch when you peer through the lens, looking outward across millions of light years. Once you spot it, the math is undeniable. Space is swelling but not expanding into anything. There is no physical edge or outside room. Space simply multiplies, carrying the entire observable universe along for the ride. This solves an old astronomer riddle: why the sky gets dark. We have plenty of stars out there, but the stretch pulls their light so far red it turns invisible. Over eons, the growing void has cooled the background radiation, stretched out old starlight, and blown distant galaxies apart like dust in a breeze. Yet even with all that drift, I can still connect with the cosmos through light. The tiny photons hitting my observatory sensors are ancient, exhausted travelers, stretched by the void but still whispering their long journey. They show me a system in endless motion, star clusters sparking, suns burning out, and galaxies softly drifting. While this steady expansion guarantees total isolation billions of years from now. It grounds me, it proves to us that nothing is truly frozen. Not even the empty vacuum. The deep sky is a living, breathing machine, with a past and a fate just as enormous as the stars. Watching space tear apart can feel pretty lonely through the eyepiece, but honestly, I find it quite poetic. Things aren't flying away because they want to leave us. The cosmos is just making room for eras to unfold. Room for star systems to breathe, room for photons to cross the void, letting us catch a final, quiet look before they vanish into the dark. Down here on Earth, light feels ordinary. You flip a switch, it flashes in a straight line and bounces off the walls. But out in the deep sky, light is so much more than simple brightness. It acts as a physical record of time, stretched across the vacuum, showing astronomers exactly where things sat and precisely when they existed. And the beating heart of our daily work is redshift. Let's think about this together. Picture a passing ambulance. While it speeds toward you, the siren wails high. Once it rushes past, the sound gets lower. That is the Doppler effect. Light does the exact same trick. If a star hurries toward my lens, its color squeezes into shorter, blue waves on our spectrographs. When it retreats, the waves stretch out into longer, redder bands. That is redshift, but space hides a secret. Out there, redshift is rarely just an object driving away from us. Most of the shifts I catalog happen because the literal fabric of space is stretching. Distant clusters are not flying away from our solar system in fear. The sheer distance between my telescope and those stars is expanding, pulling the light apart as it flies. Picture light as a tiny wave surfing the cosmic ocean. As the blackness underneath swells, the wave gets longer, its peaks and valleys separate further and further. The visual color drops. A bright, sharp blue slowly decays into a deep, soft red over billions of years. All that stretching adds up. A flash from the early cosmos hits my instruments looking totally altered. That is true redshift. It is far more than a fun physics trick. It is my ruler. It measures exactly how far a galaxy sits and just how ancient that light really is. Because when we point our lenses up, we never see things as they are tonight. We see ghosts of the past. The glow from Andromeda takes over 2 million years to reach Earth. You and I are catching 2 million years of history in a single photon. Looking at the night sky means looking back in time. The deeper I aim the telescope, the older the view gets. A cluster 10 billion light-years away is just a fossil from 10 billion years ago. We are absolutely not seeing a modern map. Astronomers watch a slow, backward time lapse. Every deep red glow is a message from the ancient dark, and the longer it travels, the harder it gets stretched. This means the farthest galaxies in my scopes don't just look faint, they appear deep red. Sometimes the shift we measure is so extreme, visible starlight becomes infrared or even radio waves. It is the same light, just pulled like taffy across our growing universe. This is exactly why you and I find redshift so incredibly fascinating. When I analyze a distant galaxy through my telescope, breaking light into individual wavelengths, we measure how far it stretched. That tells my colleagues and me its exact distance and the true age of the glow we see. But redshift reveals far more than distance to us. It uncovers deep space motion, history, and our universe's shape. When Hubble first discovered this relationship, it completely transformed my field of cosmology. It proved to us the cosmos was not sitting still, it was expanding. Almost every galaxy I track is drifting away. The further out I look, the faster those star systems race into the dark. That single observation showed our community that the universe actually had a beginning. A moment when all matter sat tightly packed together, what we call the Big Bang. Now, I use redshift to peer deeper than ever. The James Webb Space Telescope was built for infrared light, making it my favorite tool for spotting high redshift galaxies. The ones stretched the furthest, these are the very first galaxies to form after the Big Bang. That ancient light traveled over 13 billion years. Stretched across time, bearing the imprint of a young cosmos learning to shine, but it carries a melancholy truth. As space expands faster and faster, light from endless galaxies gets stretched until my instruments can no longer detect them. Their signals dim, their details vanish. Eventually, our sky becomes quieter and darker. Someday, even light from our closest galactic neighbors will fade beyond reach. The cosmic history I study will slowly vanish, not by destruction but through sheer distance. Yet tonight at my observatory, light continues arriving. Ancient photons from dead stars drift across the void, landing gently right here on my sensors. They carry a galaxy's chemistry, motion, and temperature. Some light traveled before Earth existed, some began its journey while dinosaurs still roamed. And some light is only just leaving its star, destined for another astronomer billions of years from now. I find it beautifully humbling that light is both a map and a memory. A map of where celestial bodies sit, and a memory of when they lived. Every photon is a tiny time traveler. When I look up and catch it, I am not merely observing stars. I am reading a beautiful story written in color and stretched by age. Redshift reminds me that everything I observe is already gone. But in a way, it remains with us, carried forward by starlight, completely frozen in the moment of its birth. Ultimately, redshift is more than my daily measurement. It is a language, the quiet language of a universe stretching, growing, and constantly evolving. And though our past may be fading, its echoes remain. In every beam of starlight, in every spectrum I measure, inside every red glow from a distant, ancient galaxy. When you and I talk about the universe beginning, we usually picture something vast and explosive. Stars flaring, sudden galaxies, a massive cosmic fireworks show. But as an astrophysicist, I know the truth is stranger. It began incredibly small. So small, in fact, my models show its earliest moment was tinier than a single microscopic atom. And incredibly hot, too. We are looking at temperatures reaching trillions upon trillions of degrees. A seething quantum froth so intense that the physics I study simply wobble and blur. This was no quiet birth. It was a roaring storm of pure energy. This first instant we astronomers call the Big Bang was not a traditional explosion. Nothing exploded into empty space. Instead, space itself began expanding. Space did the stretching, carrying raw energy, matter, and time along for the ride. Within the tiniest sliver of a second, less than a millionth of a trillionth of a trillionth of a second, the cosmos underwent an astonishing growth spurt that my colleagues call cosmic inflation. Imagine blowing up a balloon, but it suddenly inflates far faster than the speed of light. This breaks no cosmic rules. It is not matter moving through the void, it is space itself expanding. During inflation, quantum fluctuations, the tiny jittery blips I study in the vacuum of space, were stretched and frozen. These invisible fluctuations became the seeds for absolutely everything. So you and I, the planets, the stars, we all started as tiny quantum wrinkles inside an inflating balloon of space. Once inflation stopped, our cosmos kept stretching, just a bit slower. That fierce energy finally cooled enough for real matter to take shape. Quarks locked together into protons and neutrons. Within minutes, they fused into the very first nuclei, mostly hydrogen, a little helium, and just a tiny dash of lithium. But the cosmos was still fiercely hot and thick. Think of the core of a star. When I look back at this era, there was no clear, starry night, just the blinding interior of a cosmic furnace. Particles of light, what we call photons, were endlessly crashing into electrons, scattering everywhere. A bright, blinding fog of radiation. Then, roughly 380,000 years after the start, something absolutely beautiful occurred. Things cooled down just enough for electrons to lock into orbit around those nuclei, building the very first atoms. Light finally broke free. This exact moment left a faint hum, the cosmic microwave background, something my colleagues and I still measure today. You and I are looking at the oldest light in existence, a perfect snapshot of our baby cosmos taking its first breath. But there were no stars or galaxies in my field of view yet. Those needed hundreds of millions of years to slowly ignite. What we had was pure structure, the cosmic scaffolding, just tiny microscopic shifts in density. Those leftover wrinkles from inflation meant a few pockets held slightly more matter. As eons passed, gravity slowly got to work. Gravity gently tugged at those heavy spots, dragging in more dust, building the vast cosmic web I map in my research. So how tiny was that early space? If we rewind my models to the very first moments, the whole thing was likely smaller than a single proton. And yet it held the entire blueprint for everything. Every single star, every distant galaxy, every human thought, all of it packed into that impossibly tiny, blazing hot origin. I find it deeply poetic. The grandest thing we can observe started out smaller than the tiny pieces inside an atom. As space stretched and cooled, real complexity bloomed. Quarks became stars, stars forged planets, and eventually planets gave rise to us. All of it unfolding over billions of years from one moment of blazing simplicity. Honestly, as astronomers, we still do not fully understand the Big Bang. My colleagues and I are still chasing answers. What actually sparked inflation? What existed before that moment, if time even existed? Is our observable universe the only one out there, or just another bubble popping up in some endless cosmic sea of creation? What the math does tell us is this: space didn't need to start out massive to become majestic. It just needed physics, a bit of time, and infinite room to expand. When I sit at the observatory looking up, I am watching the direct aftermath of that fiery spark. Massive galaxies slowly spinning in spirals, nebulas softly glowing. Distant planets quietly orbiting their suns, all of it tracing back to a speck that could have easily fit in your hand. Could you and I really hold the entire universe in our hands? It hurts the brain to think about. Human minds aren't built to jump from subatomic scales to cosmic ones. But the cosmos never demands our perfect understanding. It only asks for curiosity, and maybe a quiet awe for how something so impossibly vast grew from a space so wonderfully small. But what does it really mean to be big? We throw that word around a lot. Big houses, wide oceans, grand theories. Out here, the universe breaks the very concept of size. It is not just vast or giant. The night sky might actually be infinite. Or it could just be unimaginably large. But exactly how large? And can space be massive without ever hitting a physical edge? Stick with me, this is where the physics gets strange. Let's tackle that edge question together. Most folks imagine outer space as a giant sphere. Picture a massive, dark snow globe with galaxies drifting around inside it. It is a comforting thought, but the data says otherwise. Based on my observatory readings, space does not actually seem to have a boundary. You could fly a ship forever in one direction and never hit a brick wall. There's no hidden border or sign saying the universe ends here. However, that doesn't strictly mean the cosmos is truly infinite. It might be finite, just completely boundless, similar to the Earth. You can hike in one direction forever without falling off, yet you're still stuck on a measurable globe. Space is simply curved in a way that perfectly loops around. Finite but unbounded is a very real theory for our cosmos. In our astronomy departments, we discuss this purely as geometric shapes. We model 3 possible shapes for the universe: flat, open, or closed. These don't mean hard physical walls, they define how spacetime bends. A flat universe keeps parallel lines perfectly parallel, exactly like an infinite sheet of blank paper. This version of reality would be infinite, just stretching endlessly out into the dark. Looking at the cosmic microwave background data, especially readings from the Planck satellite, our cosmos actually seems incredibly close to flat. Maybe not absolutely perfect, but the margin of error is so tiny that my equipment hasn't found a real curve yet. Meanwhile, an open universe bends outward like a saddle. In that model, our starry expanse expands forever. As an astronomer, I sometimes picture a truly infinite universe. It never loops back. If you flew in a straight line forever, you would never return to where you started. You would just keep going. But a closed universe curves inward, much like the surface of a sphere. In that model, we know space has a strict limit. Fly straight for long enough and you would eventually end up right back home, though that trip might take longer than the universe has even existed. No edge to find, just a giant cosmic loop. Now, you and I are going to get philosophical. Even a finite cosmos is mind-bogglingly huge, and if it turns out to be infinite, well, it never ends. That means endless galaxies, endless stars, endless planets. And though my colleagues debate this, maybe endless versions of you. Somewhere out in that dark sea of endless cosmic possibilities. There could be another you listening to me right now, pondering the stars, just wearing different socks. The main issue with infinity is that it breaks all human logic. I can define it mathematically, I can balance the equations, but actually feeling it is slippery. You cannot truly picture infinity. We only orbit the idea, trying to grasp what a never-ending sky actually means. Even if our universe goes on forever today, it probably did not start out that way. At the Big Bang, everything was squeezed into a brutally hot, dense state. It might have been an endlessly dense singularity, or just a tiny, contained little pocket of space. Either way, the important data point is that it started stretching, and it never stopped. This cosmic expansion gives my field another headache. Space is still stretching out, and it is speeding up every single day. This stretching does not form a wall, it simply means more empty distance appears between objects. Galaxies are not rocketing away like shrapnel from a bomb. The very fabric of space is widening, dragging star systems along like raisins baking in rising bread. As the cosmos stretches, more of it slips past the limits of our strongest telescopes. Not because those stars vanish, but because their light will simply never reach my lenses. This leaves us an observable universe, a bubble 93 billion light-years wide, where we can actually see and map things. But beyond our vision, the unseen cosmos could be vastly larger, maybe infinite, maybe not. Some models I study, especially early inflation dynamics and string theory, suggest we might just live in one tiny pocket of a massive multiverse. Each has its own rules, space, and time. If that is true, the word big falls completely short. Our home could be just a single bubble floating inside an endless sea of them, all endlessly growing, colliding, or branching away. But let's bring it back home. Inside our own sky, measuring size is really just a test of human comprehension. Whether space goes on forever or is just too huge to cross, the feeling is identical. We are small, wonderfully, beautifully small. Not pointless, just tucked into something way beyond normal human scale. I find poetry in the unknown, asking how big the cosmos is and accepting that the true number might always stay out of my reach. That mystery does not make astronomy boring, it makes it thrilling, because as long as the dark stays quiet, we keep looking up in wonder. So does outer space ever stop? I do not know, maybe it loops, maybe it stops. Maybe it stretches forever into zones my telescope will never catch, but here is what we know. Even without a hard wall, the cosmos gives us limits to push, theories to test, stars to chase. And in the pure dark of the sky, that might be the best kind of massive. Billions, trillions, quadrillions. I write these digits down easily, and the math works out perfectly. But once I chart anything past a few thousand, a weird shift happens. The scale stops feeling real. They turn into magic spells rather than hard data. We speak the terms, we grasp the abstract logic behind the math. But we do not feel them in our bones. There is a simple reason. Human brains were not built to tally up galaxies. We evolved to climb trees, hunt for food, gather fruit, and find our way through dark woods. Nature gave us a brain tuned for the physical present. You know what 10 apples look like, maybe even 50 or 100. But 10 billion suns glowing at once, that breaks the mind, it is simply scale. We like dealing with things we can see and hold. A rock in your hand, a river to walk across, a single 24-hour day. Once the chart hits thousands or millions, human intuition fails. A billion or a trillion just fades into scientific background noise. You and I can test this. Picture 1,000, got it? Now try 1 million, it blurs, right? Now jump to 1 billion. Somewhere during that massive leap, your mental map probably turned into a blurry fog, and it is not just distance. Time, too, becomes incredibly slippery. You and I can easily picture a few decades of history, maybe even centuries. But when my colleagues and I track stars born 4 billion years ago, or starlight traveling for 13 billion years, the mind just quietly bows out. It lets those massive numbers wash over us without truly feeling their heavy magnitude. But honestly, that is perfectly okay. We simply weren't built for deep space math, so we cheat. We build tools to help us see in the dark. Metaphors, celestial models, and mental maps become our cognitive stepping stones. We shrink our vast solar system down to the size of a basketball court. We make Earth a marble, the sun a beach ball. We use grains of sand to picture burning stars, or stack simple sheets of paper to map distances across deep time. One famous cosmic analogy tries to compress all of time, from the Big Bang until tonight, into a single calendar year. Looking through that lens, every piece of human history we know fits neatly, into the final fading seconds of December 31st. Everything we have ever built, written, or dreamed, all packed tightly into the very last tick of the cosmic clock. In the observatory, we also use charts, diagrams, and time-lapse animations that slowly zoom out from Earth to the observable universe's edge. These visuals are vital. They translate pure magnitude into gentle motion and cold numbers into human feeling. We even develop logarithmic thinking. That means scaling massive numbers down exponentially, gently compressing vast galactic differences into something we can sketch on a single page. It lets us compare a tiny proton to the width of a galaxy without needing a football field to write the math. Logarithmic scales are everywhere in astrophysics. From tracking quakes to ranking a star's brightness, they don't shrink the universe, they just make it graspable. Still, even with all our powerful telescopes, it is deeply humbling to try and wrap our minds around the cosmos. Consider the Voyager probe. It has been drifting in the dark for over 40 years, billions of kilometers away, yet it hasn't even crossed the final edge of our solar system. And that is just our local neighborhood. Beyond lies deep space, the stars, the galaxy, distant clusters, and the unfathomable web of everything. An astronomer's brain stumbles under the sheer weight of it all, yet we keep looking up. We teach our children what a light year is. We build quiet planetariums. We launch massive telescopes into orbit, not just to see, but to deeply understand. Somewhere deep inside human nature is a quiet compulsion to expand our mental map, to keep gently pushing against the edges of what we can comprehend, and this reaches far beyond astronomy. It touches empathy, economics, and ecology. Whether we study the wealth gap, global species counts, or the vast scale of climate change, we constantly hit walls of sheer magnitude. Data points that are technically understandable, but completely emotionally invisible. Knowing that 8 million tons of plastic wash into the ocean every year is one thing. Truly feeling the weight of that reality is something else entirely. So we build narrative stories, we create soothing comparisons. We map out what 8 million tons looks like in garbage trucks, or how many decades it would take human hands to clean up. We try connecting scale to something intimate, because that is the real secret here, personal connection. When cosmic scale becomes personal, it finally becomes visible, and once we can see it, we can reflect on it or just feel genuine awe. So no, I might never fully grasp what 10 trillion kilometers looks like, or what 100 billion spinning galaxies truly means. But we can stand beside those massive numbers, lean against them, and let them stretch our nightly imagination just a little further than before. In doing so, we gently stretch the limits of our cognitive comfort zones, not to conquer the vast cosmos, but to live peacefully within its quiet immensity. The celestial numbers will always remain enormous, but we don't have to shrink down in the face of them. We just have to learn how to listen. Come with me for a second. Imagine standing on a quiet beach under a wide sky. Between your feet and the dark horizon sit billions of tiny grains of sand. Now, picture this slowly. For every single grain of sand across Earth's beaches and deserts, my telescope sees more stars in the universe. Not just more, but unimaginable orders of magnitude more. Those burning stars aren't just uncountable. They entirely outnumber the human metaphors we have for describing them. As stargazers, we steal simple metaphors from the waking world we know. Time, travel, buildings, even fruit. We use anything to shrink the deep cosmos down into a space our minds can safely walk through without getting totally lost. Because while my calculations are highly accurate, human brains need more than raw data. They need story. Think of Earth not as a rocky planet, but a tiny speck of dust floating inside a vast cathedral. That grand cathedral is our galaxy. Immense and dimly lit, its vaulted ceiling veiled by drifting interstellar dust clouds. Our tiny speck drifts in a quiet corner, orbiting a single candle flame, the sun, while far above and all around us, countless other distant candles flicker. Through my telescope, some barely glow, others flare bright, then just vanish. The scale baffles us astronomers, so let's look at this together. Metaphors give us that sense of sacred smallness, mapping out deep time. Picture compressing the whole universe's lifespan into one calendar year. The Big Bang strikes at midnight on January 1st. Modern humans wouldn't show up until late December 31st, barely 30 minutes before midnight. Every recorded observation, every city, song, and story fits into those final few seconds. All our history is a mere whisper in cosmic time. Think about money next. If $1 million equaled a single second, a billion would last over 11 days. A trillion takes nearly 32 years. Now look up at 2 trillion galaxies. The math breaks my brain too, but the comparison helps. Distance works too. Light flies at 300,000 kilometers per second. Riding that light beam, you would pass the moon in just over a second and hit the sun in 8 minutes. The closest star takes over 4 years. Hitting our galaxy's center requires 27,000 years, and that is just one galaxy out of 2 trillion. As astronomers, we need these comparisons. Otherwise, the raw data just floats like driftwood, present but totally unanchored. They make the infinite feel real. Even kids know a single grain of space dust means something vastly different than a whole mountain of it. Someone who has never looked through an observatory lens can still feel a galaxy's weight when I call it a swirling city of stars. We don't just do it to feel small, we do it to feel connected. Stories anchor us in the expanse. Carl Sagan's pale blue dot speech isn't just astronomy. It is pure poetry. Earth is a mote of dust suspended in a sunbeam, home to every king, poet, sinner, and saint. That image didn't shrink human history. It expanded our minds, even while proving how physically tiny we are. My daily work thrives on precise math, but human minds crave pattern, rhythm, and analogy. Equations only tell half the story. Emotion, color, and shape fill the gaps. Saying the cosmos spans 93 billion light-years across is just a cold, technical fact. But if I say the Milky Way is the size of a coin, the observable universe still stretches wider than Earth. You and I can actually feel that in our chests. I don't stop at size. I call black holes whirlpools. Time flows like a river. Space acts like a fabric. As a scientist, I know these are technically flawed, but they get us close, building a mental scaffold we can safely climb. They let us stare into the void without blinking. Even the word universe is a metaphor. It implies a single, turning, unified space, yet my telescope reveals absolute multitudes. Galaxies drift like islands, stars pulse with thick nuclear fire, dust clouds forge fresh suns. The imagery works even as our data multiplies. In my lectures, these ideas act like lanterns. They light up dark cosmic corners we'd otherwise miss. Not because they map the physics perfectly, but because they offer an anchor, a way to stay mentally grounded while floating through infinite space. Great astronomy voices like Neil deGrasse Tyson, Brian Cox, and Sagan use comparisons like careful sculptors. They literally chisel meaning out of the void. They let us feel cosmic scales without getting crushed, but to astronomers, metaphors aren't just poetry. They are vital tools. Without them, the night sky is silent. With them, space becomes a story with shape, character, and scale. So how do I study a void too huge to picture? I compare it to human things: a single breath, a footstep, a speck of dust, a calendar year. Slowly, piece by gathered piece, I build a mental bridge connecting my finite human mind to this infinite, sprawling universe. I may never cross it fully, but just standing on that first plank sparks pure wonder. Stick with me here. Picture a universe running inside a computer. Not just an isolated galaxy, a lone star system, or a local solar neighborhood. I mean an entire cosmos stitched together by raw code and equations. It doesn't burn physically, but it evolves, collides, and expands just like our real night sky. This is what we call cosmic simulation. It is hands down the most powerful tool I have for answering seemingly impossible astronomical questions. I can't exactly put the real physical universe inside a lab to experiment on. I cannot fast forward an actual galaxy to watch it slowly age and evolve. I can't rewind time or tweak gravity to test my theories, but inside my servers, I absolutely can. That is the magic of these simulations. They are massive digital test tubes filled with virtual matter, constrained by real physics, and powered by Earth's fastest supercomputers. The beating heart of my models relies on gravity. Thermodynamics, the behavior of dark matter, and fluid dynamics. Tonight, you and I are going to build a universe. I start with a digital box, an imaginary cube of space 100 million light-years across. I fill it with tiny matter particles and let physics take over. Over time, gravity pulls it all together. Star systems spin up, glowing filaments emerge, and vast voids open wide like cosmic lungs. We watch reality grow from scratch. One of our most famous efforts as astronomers is the Illustris simulation. Released in 2014, it mapped a slice of the cosmos using 12 billion resolution elements. That means 12 billion distinct chunks of space, each tracked with painstaking precision. I can watch gas dynamics, star formation, and black hole feedback. Illustris gave us galaxies that looked eerily real, close enough that we finally started asking deep questions about why they form that way. Then came Illustris TNG, the next generation. Expanding our scale to create truly lifelike structures, it showed us how black holes could actually shut down star formation. I watched galaxies shift over billions of years, while the cosmic web stretched across truly unimaginable distances. Another landmark project we use is the Millennium simulation. Finished in the early 2000s, it tracked over 10 billion dark matter particles across a massive 2 billion light-year span. That is a digital box holding a massive slice of the observable universe. The Millennium Run helped us understand how massive structures form, not just individual galaxies, but entire walls and superclusters. Beyond the hard numbers, my simulations are undeniably beautiful. They render out like cosmic lava lamps. I see glowing threads connecting brilliant nodes of matter, folding and breathing like a living thing. I am not just looking at data. I am watching a story unfold across billions of years in 3 dimensions. That feels truly profound. Here is where you and I find the magic. When my models match the sky, our physics is right. When they fail, we miss something vital. Either way, they refine our understanding. They taught me how vital dark matter is. Without it, my simulated galaxies just fall apart. They refuse to clump naturally. I never see elegant spirals or dense cores. The code confirmed that something invisible, something far more common than normal matter, is quietly sculpting our cosmos, and it is not just dark matter. My screens have shown me galaxies colliding, and black holes dictating where stars are born. I see how violent early expansion formed the delicate web. These computers are my laboratory for testing ideas I could never watch in real time. But perhaps the most remarkable thing about my daily work is not just the sheer accuracy. It is their intuition. They breathe life into dry math. They let me witness physics as poetry. Gravity becomes a sculptor, shaping filaments. Gas becomes paint, swirling into grand galaxies. Energy becomes motion. Time acts as a chisel, carving complexity into simplicity, then back again. Some are interactive. I can fly through them, pause time, and zoom around. I click on galaxies to see their histories, mergers, and starbursts. I easily trace one cluster's lineage back billions of years. It feels like rewinding the entire universe, then simply pressing play from any angle I choose. But we do not build these overnight. A single simulation run can take months, demanding the combined power of thousands of processing cores. It feels like launching a rocket built of math. I hit run and wait while the numbers evolve, hoping the output resembles the night sky sitting right above my observatory. Sometimes it fails. Sometimes I get too many dwarf galaxies or stars forming way too fast, but these are not failures. They are clues. They highlight blind spots in my research, whispering about missing puzzle pieces. Because I can rerun, tweak, and test these models again, they act as massive engines of deep discovery. They help me narrow down the physics. They let me see not just the universe I study, but what might have happened if early conditions were just slightly different. They let me visualize the unseeable. I cannot directly observe the full 3-dimensional structure of the cosmic web. I only capture snapshots from my lonely vantage point inside the Milky Way. But models reveal the full pattern, the hidden architecture of dark matter, the grand skeleton of our universe. As technology advances, we are quickly nearing a point where my virtual universes look absolutely indistinguishable from the real telescope data I pull down. Some are so precise that my colleagues and I calibrate new observatory instruments on simulated skies before ever pointing them upward. Think about the deep irony here. You and I usually view computers as cold, lifeless machines. But through these models, my colleagues and I create some of the most vivid pictures of deep space ever made, images that pulse with realism and imagination. Because in my line of work, simulations are much more than code. They are translations, taking the raw math of space and turning it into something you and I can watch, explore, and feel. By doing this, it brings us closer to understanding not just the night sky, but our actual place inside it. Long ago, people literally believed the entire universe revolved around Earth. The stars danced across the dark sky simply because we were standing completely still. Planted right at the center, the sun, the moon, the wandering planets, they all circled Earth like royal subjects. And we, the supposed crown jewel of creation, just watched. That geocentric idea was born from pure observation, not arrogance. Looking up, it truly seemed like everything moved around us. For thousands of years, that illusion held firm, a comfortable, reassuring cosmic stage built just for us, but science relentlessly edits the story. Eventually, a fellow astronomer pulled back the curtain. Enter Copernicus. Back in the 16th century, he dared to suggest the sun sat at the center, not our Earth. A radical shift that finally pushed humanity out of the spotlight. Then Galileo pointed his telescope upward, watching distant moons orbit Jupiter instead of us. Soon after came Kepler and Newton. Suddenly, the entire machinery of the night sky turned on entirely new gears. This shift was more than just astronomy, it was deeply philosophical. It revealed a hard truth: we are not the center, not of our solar system, the Milky Way, or even the observable universe. In my field, we call this the Copernican principle. Its core idea is quite simple. We are not special, there is nothing truly privileged about our location in deep space, no throne at the center. No divine spotlight, just a rocky planet orbiting an ordinary star, tucked in a quiet corner of a typical galaxy among trillions more. I know it sounds harsh, like being handed a note saying you are here, and it doesn't really matter. But there is another way to read that note. Modern cosmology embraces this quiet humility. It is certainly no punishment. It feels liberating. The laws of physics apply equally everywhere. The exact same forces and beautiful math govern galaxies a billion light-years away, just like they do your warm cup of tea. We don't live in a cosmos made specifically for us, but we live in one we can finally understand. And that is truly astonishing. We might not sit at the center, but we map the stars anyway. We measure the faint microwave echo of the Big Bang. We build giant telescopes peering back 13 billion years. We simulate entire dark matter structures on massive supercomputers. In a way, we aren't the center of space, but we remain the center of perception. Think about this paradox with me. By observing the deep universe, we actually shape its meaning. The more my telescope reveals our tiny size in space, the more extraordinary it feels that we can comprehend any of it. Human brains evolved to throw spears and pick berries, not to grasp quantum fields. Yet here I am, counting photons from distant galaxies, debating the curvature of space-time, wondering if the universe is truly infinite or just massive. That ability is what makes us special, not our location, but our intense curiosity. I find real beauty in letting go of the myth that we are the center of everything. The universe isn't about us, yet we belong to it. A tiny thread in a vast cosmic fabric, a brief flicker in deep time, yet still able to look up and wonder. Think about it, you are not the center of the forest, but that never makes the trees any less beautiful. You are not the center of the ocean, but you can still float, swim, and feel the heavy cold waves. Deep space was not built for us, but it allows us to exist, observe, and ask questions, making us a vital part of its ancient story. Before modern observatories, ancient people looked up and saw star patterns, myths, and seasonal guides for their crops. They weren't claiming the universe, they were just trying to understand their place within it. That is what astronomers still do today, just with bigger telescopes and larger questions. Are we the center? Not exactly. Not in that ancient, divinely favored way where everything orbits us, but maybe we are the center of our own experience. A living lens for the universe to see itself, a small patch of consciousness blooming on a quiet, drifting rock. And maybe that is enough, because staring into this vastness, I realized something remarkable. Meaning doesn't demand a central throne, it comes from curiosity, from the deeply human act where you and I look up and ask what else is out there. So, while this massive universe may not actually revolve around us, as an astronomer, my thoughts still reach to those furthest cosmic edges. Maybe that makes the entire journey worthwhile. You and I are going to tackle a beautifully simple question tonight: how big is the universe? Yet the more data I gather to answer it, the more it slips away, like trying to catch a solar wave in a coffee cup. Maybe the question is flawed, not because astrophysics doesn't care, but because it comes from a place our human brains simply weren't built to map. Big means something concrete when we measure roads, mountains, cities, or even the planets I study. But once I look into galactic territory, out past the clusters, superclusters, and dark matter filaments, and out into the void beyond our observable edge, the word big loses all its meaning. How large is something with no boundary, no edge, no final stop? The cosmos might be infinite, or finite but unbounded, like a sphere's surface stretched across dimensions my equations can barely picture. It might just be a single drop in a vast multiverse. Even if my colleagues and I finally calculated a number, a true cosmic diameter, it would already be outdated. Deep space constantly expands. Starlight travels, horizons stretch away. There are no static measurements in this unfolding cosmos, so maybe the better question isn't how massive it is, but how does it feel living inside something that enormous? As an astronomer, it feels incredibly humbling, even a little dizzying. But it also brings a strange, quiet peace. Because once I accepted that the universe's scale is fundamentally beyond us, that no telescope, supercomputer simulation, or dataset can truly hold it, I saw something else entirely. I realized that awe and pure wonder aren't a failure of science. They're the only truly logical responses. Charting the cosmos is a noble pursuit. Deciphering its laws is deeply thrilling. But letting the sheer scale overwhelm you, that is its own quiet wisdom. We often treat scientific knowledge like control, but up in the observatory, knowledge leads us straight into beautiful mysteries. The deeper into space I look, the more complex the orbital patterns become. The wider the gulfs, the older the light. The more data we gather, the more we see our ignorance. And right there, in that soft, silent gap between my questions and answers, lies a dark sky beauty that simply doesn't need to be solved. There is deep poetry in accepting we will never perfectly map out the totality of our cosmic home. That my lenses will never capture every galaxy. That more stars will always hide behind time and deep space than hit my retinas. And yet here we sit, a tiny species on a spinning rock, staring into the black, building massive mirrors to stretch our sight, and crafting stories. Orbital equations and theories about what's out there. Even if the universe defies absolute measurement, we keep focusing our lenses, we keep wondering, we keep asking. And that is beautifully cosmic. Let's look at a paradox at the heart of this together. The more I zoom my telescope out, the stronger the quiet pull inward gets. Staring into the deep void makes you reflect on the gentle, fleeting nature of your own breath and memories. The cosmos doesn't give us verbal answers, but it proves that everything changes. I watch dying stars fade out, knowing cosmic time flows onward whether we chart it or completely ignore it. Strangely, I find that deeply calming. If the observable universe is too massive to pin down, then maybe it's just too big to worry over. My daily stresses, the creeping anxieties, the endless research deadlines, they all shrink away under the starlight. Not because they don't matter, but because they are beautifully temporary, like an eclipse. There is immense peace in letting go of needing every answer. You don't need my astrophysics degrees to feel the cosmos. You don't have to calculate the light years between galaxies to simply enjoy the soft, quiet glow of a clear night sky. You don't need to memorize redshift formulas or parsec conversions to feel moved. The simple fact that ancient starlight travels for billions of years just to touch your closed eyelids is enough. Sometimes the only rational response under the dome is to breathe in and just feel small, safe, and still. So perhaps my ultimate question isn't how massive the universe is, it's how open we are to its wonder. It's a softer hypothesis. It demands no hard data, it just invites a quiet moment. And if you and I let that moment pull us into sleep, dreaming of spiral galaxies and glowing nebulae too vast to count, then maybe the cosmos is doing its job. The night sky isn't just a puzzle to solve, it's there to gently cradle you, whispering in ancient photons, quietly reminding us that there is infinitely more out there than we will ever map, and that knowing that is enough. So go ahead, close your eyes tonight. Let your mind drift past the moon, beyond the exoplanets, right into the humming silence between stars. Picture that massive cosmic web stretching beyond my telescope's reach. Imagine distant galaxies blinking softly in the deep dark. You were never meant to hold all that data in your mind. Just let it brush against the edges of your awareness, like gravitational waves washing against a dark shore. And maybe that is the only answer we truly need. Can my field ever truly comprehend the physical size of the universe? Probably not, at least not with rigid astrophysics, not with numbers, datasets, or measurements alone. Not by stacking trillions of light years like building blocks, hoping it forms a model we can finally squeeze into our human heads. The cosmos is too vast, too deeply layered, too strange for simple answers. But through my telescope, I've learned that doesn't mean it's unknowable. Understanding space doesn't always require pure math. Sometimes the connection is purely emotional. We can feel the universe rather than just solve it. When you step outside the observatory on a clear, crisp night and look up, you don't need my astrophysics equations to feel small, quiet, and completely amazed. You simply feel the weight of it in your chest. Like something massive, a rogue planet or dark nebula, has brushed past your awareness. A quiet, unnamed presence in the night sky that leaves you completely still. In our field, we always ask if the human mind can truly grasp cosmic scale. After years of looking through the lens, I think the answer is no and yes. No, because our earthly brains weren't built for this. We weren't wired to process light years, massive galaxy clusters, or an endlessly expanding void. We evolved to track animals and find shelter by dusk. The night sky never owed us an easy explanation of its mechanics. It just needed to exist, and yet, yes, because we scientists found ways to push past our earthly limits. We built massive radio telescopes and run complex simulations. We launched tiny probes into the dark and caught the fading whispers of the Big Bang. We mapped the cosmic microwave background hum of creation. We taught ourselves to marvel, and that wonder is a beautiful form of understanding. It's not the kind of astronomy data I can log into a spreadsheet. It settles deep in your bones, resting quietly like ancient starlight pooling upon a still, midnight pond. True cosmic comprehension doesn't always mean perfect clarity. Maybe it looks like stillness, pure acceptance, and deep awe. You don't need my degree to feel part of the solar system. You already are. We are brief arrangements of atoms in a vast cosmic timeline. We are literal stardust with dreams. We are the universe observing itself for a fleeting second, a tiny ripple in an ocean of space and time. So please, don't worry if the scale is too much to picture. Don't stress if the light years and parsecs blur together in your mind. Let those massive astronomical numbers simply dissolve into soft starlight. Watch the spiral galaxies drift past, slow and silent like bioluminescence in a dark sea. Let the deep mystery hold you. This isn't a puzzle we must solve. It is simply a place to float. Close your eyes now. Imagine drifting weightless and unhurried through a quiet sea of stars. We have no final destination here, just starlight, vast orbital distance, and the incredibly gentle unfolding of deep time. Out here in this quiet darkness, maybe that is where the truest kind of understanding lives. Thank you for joining me at the telescope tonight, for following the thread from Earth to the edge of the observable universe and out into the places we can only dream of. I appreciate your curiosity, your patience, and your willingness to sit quietly with astronomical mysteries that lack easy answers. You and I aren't alone in this wonder. All over the world, fellow sky watchers are looking up right now, asking, how massive is all of this? Where does deep space end? What does it actually mean? Maybe tonight, as you drift off to sleep, you'll take a little piece of that celestial wonder with you. A sense of cosmic scale that isn't about miles, but deep feeling. A quiet peace that comes not from having all the data, but from knowing you belong to something beautifully vast and still expanding. Rest well now, dream of swirling galaxies. Let the night sky keep watch.